Okay, this one's the one where quite a lot of marks are lost, and I think would be quite hard to actually work through if you make a mistake. The mark scheme is particularly awful for working this through. I still can't share the mark scheme with you at the moment. So, what we've got is a particle that's attached at one end to an elastic string, natural length L, modulus of elasticity lambda. The other end is fixed at point A on a smooth plane. So this is a fixed point. Point B is where it actually lies in equilibrium. Now, in a minute, you'll ask about equilibrium anyway. But the point of equilibrium, it means that all the forces net to zero. Sum of all forces equals zero. That has quite a lot of bearing as you go through. There's quite a few mistakes to make as we go through. To start with, I'm going to try and work to this side. I've split up the questions a little bit because when we get down to this last section 6, it gets quite messy. There's a number of phases here, so I will need more space underneath. So let's work through the problem. First thing to notice is there is an extension. The actual natural length is here. And there's an extended part to give us our point of equilibrium, and it tells us that AB is 7/5 of L. So this extension here is 2/5 of L. So the way we can actually calculate at B, we're in, so this is part A, at B, the weight pulling down, so we've got our weight and there's the component going that way. Must equal the tension pulling up. So what we have is our weight coming down, which is mg sine alpha. Okay, so we want the sine of the alpha, which is in here. So mg sine of alpha, because we're at point of equilibrium, that equals the tension. And tension is lambda x over L. The extension, like I said, is 2/5 of L, and we know sine alpha is 3/5. So mg 3/5 of mg is equal to lambda 2/5 of L over L. Rearrange and we get lambda equals 3/2 mg. That had to be shown. You can say quote it demonstratum if you like. Now the particle is pulled down the greatest slope to the point C, where BC is 4/5 of L, and is released. Show that while the string remains taut, P moves with simple harmonic motion centered on B. So what we need to construct is a general formula for an extension. This 4/5 is a little bit misleading at this point. It causes a little bit of a distraction. So we're going to deal with an arbitrary position past B, blasting everything off. I think trying to draw things on a slope may have caused some of the problems. So that's my tension going that direction. We've extended it this way, so that's my positive x, and it's got an extra 2/5 on it of the length to get us back to the point where it's in equilibrium in B. Sorry, the natural position. So B is that way, and natural length is there. Also in the positive x direction, we have our mg sine alpha. Remember, this is actually part way actually posing down a slope, and I'm going to resolve my acceleration in a positive x direction. So the mx double dash is a negative tension plus the weight equation. Now when I put in the tension equation, I get minus lambda over L and our extension x plus 2/5 of L. Put in lambda, 3 over 2 mg, mg over L, and that gives me x plus 2/5 of L. Expand out the brackets, and what you should notice is the extension here to get to the equilibrium point should actually balance out with our component due to gravity. I missed off the gravity in the last two expressions as well, the weight mg sine alpha. So this extension part should actually cancel this mg sine alpha. So let's multiply it all out. And that's acceleration in the direction of positive x is equal to lambda, which is 3/5, 3/2 mg times x divided by L with a negative in front of it, minus 3/2 of mg 2/5 of L. So we're going to get some cancellation. We get 3/5 mg times L divided by L from the denominator, and plus m 3/5, which is the sine alpha of mg. Simplify this one in the middle, and we got minus mg, 3/5 mg is plus 3/5 mg. That's the correction for the equilibrium. The equilibrium, the stretch to get to the equilibrium is balanced by the weight of the particle. So these two cancel out. This gives me my final version of the acceleration formula as being minus 3 over 2 gx over L. Because of the statement, sorry, let's put the L with the G, because it comes in handy in a moment for the forms. We are now in the form x dot is equal to minus some kx, which is the cause for simple harmonic motion, and k is actually omega squared. Okay. So yeah, the questions here, the hard part is actually organising your diagram so that the forces resolve in the right direction. Key idea, your displacement direction should be in the same direction as the acceleration you're trying to measure overall. By doing that, you can then write your formula correctly using the right versions of the values. So your displacement is a positive x to the left, your acceleration overall is to the left. The only thing pulling us up is the tension, so that's in the opposite direction. Right, part C, calculating the time taken by P to travel directly from C to B. Now, quite a few people had one problem with this, and that was trying to work out what is the particle going to do. So we've got C, the equilibrium, and let's imagine this is a spring first. So this is just side notes, so let's do them in a different colour. And this is where some people made a slight mistake. So side colour, we've got C, B, and if this was a spring, what would happen is we go from C to B, out to the other side, come back, and that path, that journey, is one period. The question is only asking for this part, the time from B to C. So it is only a quarter of the period. How do we calculate the period? Well, it's this omega squared. The omega expression, so omega squared is everything in here that's not an x and not the minus. So it is the square root of 3g over 2l. Oh, that's the omega, not omega squared. So to be able to calculate our period, omega is 2 pi over the period, capital T. Rearrange, and I get T equals 2 pi square root of 2l over 3g. And now we want a quarter of that. So TBC is 1/4 of the T, which gives me pi over 2, the square root of 2l over 3g. Now, part C, I think was a little bit nasty because they're sort of implying that's the full starting point for the next phase. But to find in terms of L and G the time taken for it to get from this point B, so we're going from C, it goes up, it goes to B, and now after B we've got an extra little bit of time until we get to the point where the natural position is. So x is natural length. That's where my extension here, x equals 2 or minus 2/5 of L. That gets me to that point. All of that needs to be dealt with under under the SHM string mode. So to there, we are using a simple harmonic motion. After that, it continues moving up to get to our point, did they say D? Yeah, to point D. And point D is purely motion under SUVAT. It's a basic SUVAT. It's a motion under gravity. A equals minus 3/5 G. That's where we are at that point. Okay, so we've got two phases to deal with. And the reason I said this was a bit of a misnomer, this part C, is it's not truly relevant to this point. What we need is a version of the equation that uses x. And the standard version for x is x equals the true amplitude times cos omega t. The reason we're using the cos form is we started at t equals 0 at a maximum distance, A. We're at maximum amplitude. So we need to put all our variables in. We know the A from here is it 4/5? Yeah, 4/5 L. So A equals 4/5 L. Our displacement from the start. Omega we had up here, and we want the omega version. Omega is the square root of 3 over 2 GL. T we don't know, but x, where we want it to find out is this point at x. X equals minus 2/5 L. So we're trying to find out while it's still under simple harmonic motion, while there's still tension in the string, we've got this mode, this distance covered as well. So we'll find out how long that takes using the equation. So minus 2/5 of L is the amplitude 4/5 of L times cos square root 3/2 GL times T for phase 1. So we're going to calculate a T1 and a T2. Notice as I'm doing variables, I'm adding them into the diagram to make sure it's clear I'm declaring what's happening. I might say Tn time in phase n. So the first phase is simple harmonic motion, the second one is simple linear motion. Okay, so rearrange and we get cos of this angle, omega t is -1/2. In radians, when it's cos -1/2, first time it is -1/2, is in here. This is going to be at 120 degrees, which is pi for 3. Oh, it's not pi, it's 2 pi. Sorry, forgot the radians, 2 pi all the way up to here. 2 pi over 3 to give me the radians. So omega t, that's omega is 3/2 GL equals 2/3 pi. And that's in period 1. That's my omega. Rearrange, and we get T1 equals 2/3 pi square root of 2/3 GL on the bottom. I've got a feeling I've got something wrong in the L somewhere. We've got the L in the wrong place. Dimensionally it didn't look right. So going back, you get L on the numerator. Is it worth trying to turn it into anything nicer? 8/27. If I remember right, I think they leave that in their answers in their form. But that's only the first phase. Second part we've got to do is for the suvat phase. So we're now at point X. We've got a velocity, a speed going up, and we want to know when does that speed stop at 0. The acceleration downwards is going to be 3/5 of g backwards. So we're looking at we need v squared equals u squared, add on 2, no we don't, wrong suvat, because we want time, don't we? It's the simplest one. So we're going to use v equals u, add on at, and we need to calculate what this u is, the starting velocity. Now that starting velocity is a standard equation. The velocity at any point in time is the omega squared amplitude squared minus displacement squared. Okay, so we need to drop those values in to find out what the velocity was at this starting point. So ux squared is omega squared. Omega, let's hope I get them the right way up this time. Omega squared is 3/2 g over L. A is the original amplitude. Sorry, I've just been contact. So I just got a message, students were trying to contact me, so I had to pause the video. A squared, that's my the amplitude of my motion, so that's 4/5 L. X is where we got to this point of the natural length, so that is at a distance now of x is -2/5 of L. Remember our natural point over here. Can I just move that whole equation over so I've got space? -2/5 L all squared. So this is omega squared is that part. The amplitude is how far it's stretched from B. The displacement is how far, where is the natural position compared to B. That's the 2L. Drop my values into my equation and I get 3/2G/L. We've got 16/25 L squared minus 4/25 L squared. Simplify through and we're going to get 36/50 G/GL. Not over, because the L cancels with the L squared. So that's my velocity squared. So now use the Suvat equation. Our final velocity is 0. My start velocity is the square root of 36/50 GL. Speed is -3/5 sine of alpha times g, because it's trying to slow it down, and my period 2, my time 2. So everything is rearranging, moving round to give me T2. Which is, take that to the other side, we've now got 6/150th of G L to be divided by 3/5 G. There's lots of messing around in here at the moment. 3/5, we've got 30. Simplify that to there. That gives me some nice stuff to cancel on the outside. So T1, strictly there should be minuses, but they're cancelling out as well. So cancel through, and we're going to get 2 the square root of L/2/G. That's my T2 period, and the total time then from the start point, which was, let's say, 2D when it's stationary, is T1 plus T2. T1 was 2/3 pi. 2/3 pi, 2/3 L/G. All square rooted, plus my 2 square root of L/2G. You could probably take out a square root L/G, but you've still got loads of roots all over the place then as well. So I think that's probably an expression they would accept. Okay, so that was the hard question as well, the last one. Sorry for the interruptions.